A mass of 0.50 kilograms is attached to the end of a circular copper wire and swung in a circle about a fixed point. If the Young's modulus of copper is 117 times 10 to the 9th pascals, the diameter of the wire is 2 millimeters, the length of the wire is 0.80 meters, and the velocity of the mass is 5.2 meters per second, find the change in the length of the wire at both the top and the bottom of the circle. We will refer to when the mass is at the bottom of the circle with the subscript 1, and when it is at the top with the subscript 2. Now we will list our knowns and unknowns. The mass is 0.50 kilograms. The length of the wire is 0.80 meters. The Young's modulus of copper is 117 times 10 to the 9th newtons per meter squared. The radius of the wire is 0.001 meters, and the velocity at both the top and bottom of the circle is 5.2 meters per second. We do not know the change in the length of the wire at both the top and bottom of the circle. We will begin this problem using a coordinate system in which the positive x direction points to the right and the positive y points up. We will solve this problem as per usual using the momentum principle. Additionally, we will make use of what we know about circular motion. For further detail on the physics of curved motion, see section 5.7 of the 4th edition of Matter and Interactions. We will first find the length of the wire when the mass is at the bottom of its circle. We will start with the momentum principle. Since we know that at this point there are no forces acting in the x direction, we can simplify by looking only at the y component of the net force and the change in momentum. The net force in the y direction is given by the force of tension in the positive y and the force of gravity in the negative y. Thus, Ft minus mg. We know that Young's modulus is given by stress over strain, where stress is the ratio of the force of tension over the cross-sectional area of the wire, and strain is the change in the length of the wire over the length of the wire. We can solve this expression for Ft, the force of tension, and plug it into the above expression, giving us that the net force in the y direction is delta L1 over L times Ya minus mg. We will also use our knowledge of curved motion, which tells us that dpy dt is equal to mv1 squared all over L plus delta L1. Then we plug both of these into the momentum principle. This gives us an expression for delta L1 in terms of our known quantities. Now we must solve for delta L1. The first step is to get the delta L1 out of the denominator on the right-hand side by multiplying the entire equation by the quantity L plus delta L1. We will also multiply by an extra factor of L to clean things up. This leaves us with, on the right-hand side, the quantity L plus delta L1 times the quantity delta L1 Ya minus Lmg. On the right-hand side, we have Lmv1 squared. Foiling out the expression on the left-hand side of the equation gives us Lya delta L1 minus L squared mg plus Ya delta L1 squared minus Lmg delta L1 equals Lmv1 squared. We see that this expression includes terms with delta L1 squared, delta L1, and with no delta L1. This is a quadratic, which we can rearrange by grouping terms by their power of delta L1. Now pause the video and do this regrouping yourself. Our final expression is Ya times delta L1 squared plus the quantity Lya minus Lmg times delta L1 plus the quantity negative L squared mg minus LmV1 squared, all equal to 0. This is now a quadratic expression of the form ax squared plus bx plus c equals 0. We can solve this using the quadratic formula, which tells us that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in our values for a, b, and c gives us delta L1 equals negative the quantity Lya minus Lmg plus or minus the square root of the quantity Lya minus Lmg squared minus 4Ya times the quantity negative L squared mg minus Lmv1 squared, all over 2Ya. Since the cross-sectional area of our wire is given by pi r squared, all the quantities in this expression are known, and we can plug in and solve for delta L1. We find that the two possible roots are negative 0.80 meters and 0.000047 meters. The physical implication of this first result would be that at the bottom of the circle, the wire is compressed to essentially length 0. Thus, we can reject this. The second value tells us that at the bottom of the circle, the wire is stretched by 0.047 millimeters. This delta L1 is very small relative to the total length of the wire. In finding L2, we will proceed similarly. However, since dpy dt, ft, and fg all point towards the center of the circle, we will redefine our coordinate system so that the positive y direction points down. Once again, we will begin with the momentum principle and simplify to looking only at the y direction. F net y is here given by ft plus mg, where we can once again substitute in our Young's modulus result for the force of tension, giving us delta L2 over L times Ya plus mg. Here too, dpy dt is given by mv2 squared over L plus delta L2. Plugging these into the momentum principle gives us delta L2 over L times Ya plus mg equals mv2 squared over L plus delta L2. Again, we multiply the entire expression by L times L plus delta L2 to get rid of all denominators. The left-hand side becomes the quantity L plus delta L2 times the quantity delta L2 Ya plus Lmg, which we expand to Lya delta L2 plus Lmg delta L2 plus Ya delta L2 squared plus L squared mg equal to Lmv2 squared. Once again, we can bring all terms over and group by powers of delta L2. Take a moment to do this for yourself and identify the coefficients that you will plug into the quadratic formula. We obtain the expression Ya delta L2 squared plus the quantity Lya plus Lmg times delta L2 plus the quantity L squared mg minus Lmv squared, all equal to 0. Note that the only differences between our quadratic expressions are the signs of terms involving the force of gravity mg. Our expression for delta L2 will then be the same as that for delta L1 with these few sign changes. We find delta L2 equals negative the quantity Lya plus Lmg plus or minus the square root of Lya plus Lmg squared minus 4Ya times the quantity L squared mg minus Lmv2 squared, all over 2Ya. Plugging in our values gives us the two possible results, negative 0.80 meters and 0.000027 meters. Once again, we can reject the result which says that the wire compresses to a length of 0. Thus, we find that at the top of the circle, the wire is stretched by a length of 2.7 times 10 to the negative 5th meters. This result is of the same order of magnitude as our result for delta L1, and it is slightly smaller. This agrees with our intuition that at the top of the circle, the stretch should be less since the force of tension and the force of gravity are pointing in the same direction. Now for our sanity checks. Since our results for delta L1 and delta L2 only differ in sign, we only have to carry out one unit check. We have meters times newtons per meter squared times meter squared plus meters times kilograms times meter per second squared plus the square root of meters times newton per meter squared times meter squared plus meters times kilograms times meters per second squared plus newtons per meter squared times the quantity meters squared times kilograms times meters per second squared plus meters times kilograms times the quantity meters per second squared, all over newtons per meter squared times meters squared. Simplifying to newtons where possible and condensing gives us newtons times meters plus newtons times meters plus the square root of newtons times meters squared plus newtons times newtons meters squared, all over newtons. This simplifies further to newtons times meters plus the square root of newton squared meter squared plus newton squared meter squared, all over newtons, which in turn becomes newtons times meters plus newtons times meters, all over newtons, which gives us meters as we desire. For our order of magnitude check, we will look at the situation in which the mass is hanging at rest from the wire. In this case, the momentum principle tells us that Ft minus mg equals 0, which tells us that, in turn, delta L equals Lmg over Ya. Plugging in our values tells us that delta L in this situation is 1 times 10 to the negative 5th meters, which is of the same order of magnitude as our two results. In this problem, we have found that the stretch in the wire when this mass is swung in a circle is very small relative to the total length of the wire. In fact, it is so small that the quantity L plus delta L could effectively be replaced with just L. In physics, you will often make use of such simplifications. However, knowing when they are accurate is an important skill to develop.